Good morning and welcome back. Long time no see. Uh, we will finish chapter 10 using online learning mode. And after that, we still have two chapters, chapter 11 and chapter 14. Probably we will go back to our classroom. I prefer to teach you face to face so I can see your response, not just face to the screen. Face to the screen is not interesting. Face to your face feels better. Today's course, we will cover scattering. As you can see here, scattering and diffractions and diffractions. So I will first talk about scattering. I will introduce the idea of perturbation theory of scattering. Then, after that, we will talk about diffraction, section 10.5, scalar diffraction theorem. Okay, so these are new ideas. So what is the purpose of perturbation theory of scattering? We try to answer the scattering of the air. So we can explain why at the midday the sky is blue and close to the sunset the sky is red. People know this is caused by scattering, but how? I will show you step by step use the perturbation theory of scattering. Since we will consider the perturbation theorem, so we will consider a slightly non-uniform medium. So this time, the medium is not uniform, it's non-uniform. So it's epsilon, depends on position, epsilon naught plus delta epsilon x, mu x equals mu 0 plus delta mu x. That is, we have a small perturbation, very small. And you can just imagine our air. Air epsilon is very, very close to 1. And if you consider air consists of hydrogen, oxygen, nitrogen, the molecules will result in slightly change in epsilon and mu. Okay, so we call this one scatter. S-C-A-T-T-E-R, scatter plus E-R, scatterer. In section 10.1, epsilon of the scatterer can be of any value, but the solution is more restricted by the scatterer geometry. So this word is correct, scatterer. Okay. Epsilon 0, mu 0 are independent of x and t. Okay. Epsilon 0 and mu 0 are not necessarily the free space value, but here we just use the free space value. Okay, first, let's consider Faraday's law. Changing magnetic field will induce electric field. And we take curl of this term again, curl, but times epsilon 0, epsilon 0. So epsilon 0 is a constant, so here, epsilon 0, time derivative space curl can commute, so we can change the order, it doesn't matter. Okay, next one is Faraday's law with Maxwell corrections. And once again, we consider the air, so no source term, no source term, no J happy. Curl of H equals partial D, partial T. And once again, we times epsilon 0 and mu 0. Epsilon 0 here stays here. And we take partial time derivative, okay? And this one will double time derivative, okay? So we got this one. Maybe I should use laser pointer here. We got this one. And 1 minus 2. Okay, what is the purpose of 1 minus 2? 1 minus 2 give us this, and this one can be something look similar. Okay, so 1 here, this term do not change. And this term, epsilon 0, partial t, curl of B minus mu 0 H, okay, equals this one, minus 2, mu 0, epsilon 0, partial t squared D. And then we will deal with this term again, Gauss law. But remember, we have no divergent curl of D. Curl of D, these terms equals divergence, gradients, divergence D minus Laplacian D. And because of no source terms here, no free charge, so of course we have bound charge. And eventually these equations equals to this one. Okay, so you can see our purpose. We have D, epsilon 0 E. We have B, mu 0 H. Looks similar. So we can further 3 minus 4, 3 minus 4, 3 minus 4, 3 minus 4. Okay, so eventually what we have, eventually this one minus, so becomes plus 3 minus 4 becomes plus Laplacian D, and this one minus this one, so still minus mu 0 epsilon 0 partial square D partial T square, and this one minus this one, so we add a minus sign here, so it's a D minus epsilon 0 E. Okay, and last terms epsilon 0 partial T curl of B minus mu 0 H here. And because of the perturbation, we know this part can be read into delta epsilon, position dependent E. And this part, delta mu, position dependent H. Interestingly, we have a minus sign here, but here is plus sign. Okay, then we can deal with this one. This is the perturbation theory. So we can calculate D using the perturbation X and perturbation mu. Okay, so we will start from here, but in the next few slides, it's too complicated. It's advanced material, so I say it's optional. That's designed for students who works very, very hard. Okay, if you are interested, you can study by yourself. Okay, the same, optional. Here, we want to calculate the cross section of the scatterer. How to do that? We will use this idea again. And we define Q. Q is equals to K n0 minus n. N is the direction of the incident wave. N0 is the direction of the incident wave. N is the direction of scattered wave. Okay, that's it. So we will try to explain the perturbation theory of scattering to explain why the sky is blue and sunset is red. Blue sky and red sunset. So D is equals to epsilon 0 E plus P. D equals to epsilon 0 E. P consists of many dipoles. So N here means the number of molecules per unit volume. P is the dipole moment per molecule. So total N times smaller p is dipole moment density. And we know P can be written into gamma MOL. That's molecular polarizability. See equation 4.72 and 4.73. 4.72 and 4.73. Gamma MOL molecule epsilon 0 E. Okay, by doing so, substitute this term into here. We got this one. Okay, if you don't like, you can just write the macroscopic effect. Okay, that's epsilon. So epsilon is obviously equals mu 0 1 plus n gamma molecule. However, from microscopically, we may write into this form. Epsilon depends on position. Epsilon 0 plus gamma MOL epsilon 0 delta x minus xj. J is the position of the molecule. So obviously this term will be very, very small than epsilon 0. You can imagine this is a very small term. We need a lot of particles to increase the effect. Number of particles per unit volume is huge. Huge. Okay, so each one is extremely small. So obviously, delta epsilon x can be written into this form. Epsilon 0 move out, and summation j gamma MOL delta x minus xj. Okay, since epsilon x fluctuate microscopically, it depends on the position, and when we x is the same as the molecule's position, then we got the value. Otherwise, nothing. With a weak variation, very weak variation, delta x of x, we may apply the perturbation theory we just develop, substituting delta epsilon into this one and substituting 10 to 31 into 10 to 28. Eventually, we got these relations. That's the cross-section per solid angle, differential cross-section. Okay, equals k to the fourth power over 16 pi square absolute value of gamma molecule square epsilon complex conjugate dot epsilon 0 square fq. First, let me explain. K is the wave number. Okay, gamma is this one. molecular polarizability. Epsilon is the polarization of the scattered wave. Epsilon 0 is the uh, incident wave. Let's go back to the definition of this one. Give you a better understanding. Okay, here, N just represent the incident wave directions, direction of the incident wave N0. N is scattered wave, direction of the scattered wave. We assume we maybe align N to be on the XZ plane. Okay, so the angle is theta between this one, and epsilon 0 is perpendicular to N0. Epsilon 0, N0, and that's the polarization of the wave. And polarization of the incident wave. And we can divide the scattered wave into two polarization. One is epsilon, the other is epsilon 1. Okay, differ by 90 degree. So epsilon 1 is still in the XZ plane, and epsilon 2 is in the y-axis. Okay. Chapter 10 is difficult because we need some imaginations. You need to imagine. You need to have a three-dimensional understanding about this one. That's why it's quite difficult. Okay, let's go back. So we know this one here, and we know the definition of this one. So if we observer, we can choose different polarization to observe the cross section. We have a detector, for example. The detector can detect different polarization of the scattered wave. So we can detect the different differential cross section versus the incident wave. FQ is here. Summation exponential IQ xj, and xj, this one we can sum into this one. Okay, Q is the vectorial change in wave vector during the scattering. Just change. This is the incident, and this is scattered. And K is the wave number. So differential, the smaller case Q, just define in this one, or go back to this one. This line is defined here. Okay, that's our purpose. And if for random distributed molecules, just like our case, the molecule is randomly distributed. So this one will be equals to the total number of molecules because they are incoherent radiation. Only when xj equals xj prime, we have value. Only when. Otherwise, because they are randomly distributed, so no contribution. Okay, makes sense. So this one will give us number of particles because of randomly distributed molecules. Okay, so now we relate gamma MOL to the macroscopic quantities epsilon, n, and n. N equals epsilon 0, 1 plus n gamma molecule. Okay, so gamma molecule equals epsilon divided by epsilon naught minus 1 divided by n okay? And this one equals to n squared. N is index of reflection here, minus 1. And this one can be rewrite into two parts, n plus 1 and n minus 1. N plus 1, since n is very, very close to 1, so n plus 1 can be write into 2, 2n minus 1 over n. So we have 2 gamma MOL can be write into this form, 2n minus 1 divided by n, okay? So we can rewrite into this form. And we have 4 here. Okay, so eventually the sigma, the omega, k to the 4th, 4 pi square, n square, n minus 1 absolute value square. This part the same. Depends on polarization, and then total number of particles. The total cross-section, scattering cross-section per molecule. So it's per molecule. So it divided by n, okay? So divided by total number of scatterer. Total number of scatterer. So this part cancel. We have k to the 4th, 4 pi square, n square, n minus 1 square. Okay, total number. So we should integrate phi dependence from 0 to 2 pi. Phi is in the x, y plane, and theta dependence. Theta dependence from minus 1 to plus 1. The cosine theta, okay? The cosine theta, epsilon star, epsilon 0 square. We have changed the notation here. And epsilon star dot epsilon 0 is the polarization of this one and this one. So we can write into two parts, cosine pi over 2 minus theta. Pi over 2 minus theta. Okay, so it's sine theta. So in sine theta square, the cosine theta, the result is 4 over 3. 4 cancel with this one over 3 here. And this one gives us 2 pi, 2 here, pi cancel. Okay, that's the final result. Total scattering cross-section per molecule is defined by this one. It depends on number density, depends on n minus 1 square, divided minus density square, and more importantly, depends on k to the 4th. So epsilon is only epsilon 0 minus n plane for dipole scattering. We use this definition already. Okay, so looks good. Everything looks good, reasonable. So eventually, sigma is proportional to k to the 4th, and these two. Okay, reasonable. Okay, what else? We try to explain the famous effect called Rayleigh scattering. Rayleigh scattering, sigma is 2k to the 4th over 3 pi n square, n minus 1 absolute value square. I be the intensity and power per unit area of the incident wave. I is the intensity. Then di dx equals minus I n sigma. So we know what does this mean? The intensity will be blocked by n sigma. N is number density, sigma is cross section per molecule. So if we have n molecule, so this one will be blocked. That means the I will be decreased. So in other words, minus I alpha. Alpha means attenuation. Alpha means attenuation coefficient. That means it will be exponential decay. Exponential decay. So the result will be I times exponential minus alpha x. So we take x derivative. It gives us an alpha here, a minus alpha. Okay, so from this equation, you know the wave will become weak and the intensity of the incident wave from the sun will become smaller and smaller. Exponential decay because of the scattering, because of diffractions, because of the scattering due to molecules. When alpha equals n sigma, so we got this one, attenuation coefficients. So first, alpha is proportional to k to the fourth power of k. So at the violet line, 紫外线, lambda is very small. So lambda is small, k is large. So let's scatter more than red line. So from this viewpoint, red line lambda is approximately equals 650 nanometer. Violet line 410 nanometers. So the relation between this one, so you know from these two equations, k to the fourth, we know violet line is scattered more than red line. Violet line scattered more than red line by a factor of 6.3. Okay, that's very important. That is, the violet light is much easier to scatter under the same condition. Okay, because related to k to the fourth. And in 10 to 35, we have another one, n minus 1 equals 1 over 2 n gamma mol. If you are not, go back here. Okay, n minus 1 equals to gamma mol times n divided by 2, right? Okay, hence alpha will be proportional to n. Oh, we have n squared here, and we have n in the denominator. Therefore, alpha will be proportional to number density. Okay, of the same types are added or taken out. The blueness of the sky and the redness of the sunset can be explained from the following two slides. In the Earth's atmosphere, alpha is a function of x. Then the Ix over dx equals minus Ix alpha x. So Ix is position dependence. Okay, reasonable. But you know, so at the high noon, violet will be the sun the sun is about 1 times of the atmosphere. That's the integrations in atmosphere. In the midday, sun at the zenith, right above you. The midday, high noon, so sun is right above your head. So it's in the zenith. So roughly about 100 kilometers. Okay, roughly 100 kilometers here. Okay, so you perform the integration, you got these relations. Okay, so we know violet will scatter the more, red will not. Therefore, at the midday, high noon, we will receive many scattered violet, scattered blue light, but our sun radiate less violet compared with red. Therefore, we will see our sun is something look like black body radiation, and violet uh, is not that much. Although violet scattered more than the red, but after integration, after we know uh, the blue will be the dominant. Okay, let's explain why at the midday the sky is blue. However, at the sunset, sunrise and sunset, the sun will be travels through the sunlight will be travels through the atmosphere. So obviously, violet or blue are completely scattered, nothing left. Only the red light can penetrate to the atmosphere and reach your eye. So here you can see only the red light. Here, no blue light, no violet. That's why at the sunset and sunrise, you see the redness of the sky. Okay? We have two questions. Why is the sky blue instead of violet? Actually, I have explained. Second, why is it more likely to get a sunburn in the summer? Okay? Hot summer and cold winter results mostly from a different cause land in two. What's it? You can consider this as an extra bonus. Try to explain these questions. Okay, just give you a personal experience. Roughly about 20 years ago, I went to the Israel. And Israel is very hot. We went to the Dead Sea. Dead Sea is below the sea level, 400 meters below the sea level. I don't quite remember the number. And it's very, very hot. But interestingly, at the Dead Sea, we exposed to the sun, but no sunburn at all. No sunburn at all. Okay? So it's interesting. It's very hot, extremely hot. And the sun is very strong, but no sunburn. Yeah, no sunburn at all. This also, you can explain why. And if you have chance to go to the Jet Mountain, the peak of the Jet Mountain, Yushan, is about 400 meters high. And even though you have a partly cloudy day, you will be easily get sunburn. Okay, try to explain. Even though you use some protection screen at uh, broad daylight, you will get sunburn at the Jet Mountain. the peak of the jet mountain. So you can explain what happened here. So I think section 10.2 are very interesting because we can explain many interesting phenomena from simple scattering theory. Just based on the perturbation theory, we can explain a lot of phenomena. Therefore, it's very interesting. Okay, let's take a break. 30 minutes break. Drink some tea. Okay, let's move on to another subject, scalar diffraction theory. In chapter 10, we talk about scattering and diffractions. What's the difference? What's the difference between scattering and diffraction? And we will explain. And when we talk about diffraction, we will recall, we will use the green function again. Yes, the green function. And it's very useful. So I will explain this one step by step. First, let's consider the simplest case. If we have a screen here, we have a screen. This screen should be anything, plastic, metal, anything, a screen. And we have an incident light. Incident light is a plane wave, so phase in each plane is perpendicular to this one, okay? So that's a plane wave. And the incident light here, we have a wavelength, lambda. And we have a width of this hole or aperture. This hole or aperture. So you can imagine if d is greater than lambda, what will happen? We have a geometric optics. Geometric optics. That means the ray will propagate in straight line. Okay, so geometric optics tell you that. Simple. Okay. However, the edge will have some effect. When the wave hit this screen, nothing happen. But wave hinge the edge, that will result in some kind of effect. That's diffraction theory. And diffraction theory, as you can see here, the wave hit this region and hit this edge, there will be length difference. If we propagate to this point, from this viewpoint, it's impossible to propagate to this point because it's blocked by the obstacle, by the screen. But now we consider the effect of scattering, diffraction, 绕射或衍射. We know from here to here and from here to here, there is a difference. And the difference is about d sine theta. So d sine theta is the difference. If the d sine theta equals lambda, what will happen? These two, this one and this one, will be in phase, but with the middle section will be completely out of phase. They will cancel. complete cancellations occur, we will have first minima. We have maxima in the middle, first minima here. Okay, so that's physical optics. Let's consider diffraction theorem. So you just imagine the experiment you done when you are undergraduate students, freshmen, single slit diffraction or double slit diffractions. Lambda is quite small, maybe 400 nanometers or 500 nanometers, and D is about millimeter or submillimeter. So therefore, D is much, much greater than lambda. Okay, but remember, in previous sections, we always assume lambda is greater than D. So that's the major difference. So let me explain that again. Nature of the diffraction problems. Physically, the diffraction problem here is not separable from the scattering problems because they look similar. Diffraction, scattering. However, the treatment are different. The scattering problem treated in the previous sections assume lambda is greater than D. So lambda will induce electric dipole and magnetic dipole. Okay, that's the idea. However, this section we will introduce scalar diffraction theory. In this theory, is most valid when D is greater than lambda, for which it gives the next order correction of the geometric optics. That's the geometric optics. And we consider lambda is smaller than D here. That's physical optics. Okay, we will try to correct these terms. Okay, why? But remember, E field, B field is not scalar, it's vectors. So why we use scalar diffraction theory? Why? Let me explain. Why we use scalar diffraction theory? Why scalar is sufficient? Physically, the electronic responses, J and the rho of the aperture. Aperture means a small hole. This is an aperture, such as single slit is an aperture. Aperture material. When the incident wave generate electromagnetic fields in addition to the dissipating some of the incident wave. So the incident wave will generate J and the rho, and J and the rho as a source will radiate. Okay, will generate more source. And far from the edges of the aperture, J and rho physically results in refraction of the incident wave. So far from the aperture, that will generate J and rho on the screen. You can imagine we have a metal screen, and J and rho will result in reflections, normal, reflect the wave. Okay, so far from the hole, far from the apertures, the edge of the apertures, okay, give us nothing. The superpose, only when J and rho near the edge produce fields that passes to the right of the aperture. That means here the incident wave are blocked by the screen. Only here and here they will generate some kind of radiations. In the middle, almost no change, just propagate. So at this region, right-hand side, the superposed fields form the diffraction pattern. In the far wrong of the diffraction regions, far wrong, a few lambda from the apertures. This is a few lambda from the apertures. Radiation field in the far wrong. We know the field takes the form of an EM wave, which obey this one. Remember, this is our midterm exam problem. Okay, prove this one. You can see, also you can see equation 9.19. When Z0 is the characteristic impedance or the wave impedance of the vacuum. The wave impedance of the vacuum. 377. N is the direction of the wave propagation. So from here to here, or from here to here, or from here to here. And we know they have simple relation. E equals Z0 times H cross N. Okay? We have simple relations. You can express E in terms E can be expressed as H and N, or H can be expressed as E and N. That's it. Or N is related to E and H. Okay. Okay, so E, H, N are mutually orthogonal. N just the direction of pointing vector. So E cross H just represent the direction of N. That's pointing vector. The amplitude of E and H has a known ratio Z0. Therefore, one component of the fields give most of the information. Phase intensity. But remember, they do not give the polarization. But not the polarization. If we want to know the polarization, we need two components, two orthogonal components. One in this direction, the other in this direction, perpendicular to each other. If we want to know, we need orthogonal. This justifies a scalar diffraction theory for the diffraction phenomena. Okay, so we don't need everything. We just need one component. We got everything. Okay, this justifies a scalar theory for the diffraction phenomena and explains why it has been the basis of the work on diffractions. So that's why we use scalar diffraction theory. All we need is one component, EOH components, one of EOH. And then I will introduce an interesting phenomenon called Kirchhoff integral formulas. Kirchhoff integral formula. In a scattering problem, we calculate the scattered fields due to J and rho associated with the dipole moment. Remember, we calculate J and rho, but at that time, they are associated with the dipole moment induced by the incident fields. The incident field will induce dipole moment. Okay, that's for the scattering problems. Be careful, sometimes we say scattering problems, and here we say scattered field. Active voice, passive voice. This is the scattering problem, and this field is scattered by the incident wave. In the diffraction problem, the fields are produced in part by the induced J and rho on the aperture material, but J and rho do not appear explicitly in the field equations. Okay, they are implicit in the boundary conditions. So J and rho are hidden in the boundary conditions. So the Kirchhoff integral formulas expresses the diffracted fields. Okay, once again, diffracted fields in terms of the boundary conditions. So we deal with the Kirchhoff integral formula in terms of the boundary conditions. With determination of the near fields requires the accurate handling of the boundary condition. Very few cases can be solved completely. So near field is difficult. However, the far field can be fairly accurate determined with the crude boundary conditions. So obviously we will deal with the far field. Far fields can be fairly accurately determined with the boundary conditions. Okay, far fields can be accurately determined with the boundary conditions. So next one, I will introduce the Kirchhoff integral formula. Okay, refer to the figures to the right. Figures to the right. This is a side view. This is the top view. Okay, S1 is an opaque surface. This is an opaque surface, just like metal. But we have some apertures. 1 or 2 or 3 or more. If we have one, looks like a single slit. We have one slit and we have two, looks like double slit. And we have a lot of them on the screen, looks like grid. Okay, and with aperture on it, it can be any shape, but we prefer it to be a flat surface. The diffraction regions, region 2, that's the incident regions, region 1, diffracted region, region 2, region 2. Region 2 is the volume enclosed by S1 and X2. And you can imagine the surface of S2 is very, very large. Okay, so we have two regions, two surfaces. Surface 1 is opaque surface with some apertures, with small apertures. And surface 2, nothing, another surface, very large. So from a top view, looks like this one. Surface 1, we have source. And surface 2, we have nothing, no radiation source, just wave radiate from the source, from surface 1. So we can write phi xt, separated them using the separational variable. Phi x exponential minus I omega t be the scalar fields, can be E field or B field, a component of E or B. Then, Helmholtz wave equation tells us that we can separate by separated time dependent and space dependent. We have these relations. Phi gives the phase and intensity, but not the polarization. If we need the polarization, we need two components, not just one. Below, we will express phi in region 2 in terms of phi, and psi on the boundary surface. We will use the Greens Theorem. Okay, that's the Greens Theorem. Obviously, you know what's going on. We will introduce the green function. Okay, so that's the Greens Theorem. We will introduce a Greens functions, g, x, x prime, satisfy these relations. At the right hand side, we have a minus delta x minus x prime, and apply this one. Phi equals psi, phi here, and phi equals g. Okay, that's the green functions. And because of this one, we know this one we substitute here. Minus k squared phi x prime. Okay, and phi equals g. So the same. Just substitute volume integration. And here, phi here, g give us delta function. No, in addition to delta function, also give us to this one. So it Laplacian g give us two terms, not just one, but two terms. So this one give us a minus k squared g, minus sign, so it's plus. But here we have a minus, so this part cancel. Okay, so luckily we have minus, we have delta function. Delta x minus x prime times phi x prime after volume integration just give us one value, that is phi x. Happy day. We simplify the left hand side a lot. How about the right hand side? Right hand side is still the same. G is here. We have a minus sign, so we can change the order. So this part move to the front. N prime gradient prime G. This part move to the front. And minus sign move to here. The real part. Minus G x prime N prime dot prime phi. Okay? So what's next? Green function. What is the green function for this one? That's your one of your midterm exam questions. What is the solution for this one? We know if we have outgoing wave boundary condition, the solution for this one will be easy. This one. But that's for outgoing wave boundary conditions. However, here we have incoming wave in these regions, outgoing wave in these regions. So a question arises. Is this a good choice? I'm not sure, but we can try. Actually, it's not a good choice. That's the green function with outgoing wave boundary conditions. Yeah, your midterm exam question. So we can rewrite. We use a capital R. It's the separation between x minus x prime. So the green function x minus x s prime equals exponential ikr 4 pi r. Okay, and so gradient prime g give us dg dr gradient prime r, and gradient prime r we did not add gradient prime, the same. because one change with x prime, the other change with x. They differ by a minus sign. So we can change the notations. And this one equals minus r over r, okay? The g dot gradient r. We change g first and then change r, okay? And this one, the g give us two terms. We change the numerator. So we have ik exponential ikr over 4 pi r, the same. And here we have another one, minus e ikr over 4 pi r squared. So we can factor out e ikr 4 pi r to the front. So we got ik and ik here. So this corresponds to this one. Okay. And this one, we have a minus sign here, and we have here, this one, ik. And this one corresponds to this one. I cancel, so we have a minus sign. And here, r, vector r over amplitude of r. So that's a simple operations. So hence, phi x equals minus 1 over 4 pi. Why we have a minus sign here? Because of this one. We move it to the front. Here, we generate a minus sign, and we have another minus sign here. So we move the minus sign to the front. And so this one becomes plus green functions in the direction of n, okay? In the direction of n here. N prime, surface integration. And here, we just move these terms to here. Exponential ikr to here. Ik 1 plus I over kr r over r phi. What's next? We assume that phi on S2 is transmitted through S1. So phi, the radiation, the E field and B field on S2 is totally transmitted from the aperture from S1. Therefore, phi x2 will be inversely proportional to r because of the radiation fields. And the contribution to the integral of 10.77 from S2 vanished. Contribution of the integral comes from S1 and S2, but S2 is very, very far. So contribution from S2 vanished as the inverse of the radius of the sphere. Therefore, contribution from S2 vanished. Assume further that the radius goes to infinity, and hence we can neglect the contribution from S2. Because radiation field, we just consider the source from here and calculate the radiation here. Okay, then we can, this equation gives us the Kirchhoff integral formula. Kirchhoff integral formula. The same, see, n prime the same, this one the same, this one the same. Kirchhoff integral formula is a simplified version of Greens theorem. We just consider the contribution from S1. And we can calculate everything in the region 2. In the region 2, especially the far field. Okay, that's the Kirchhoff integral formula. Okay, looks okay. Everything looks okay. Phi is in region 2. Is now expressed in terms of phi and partial n, this one, on S1. That is, all the radiation in region 2 can be calculated from the source terms in surface 1. On surface 1. Reasonable. Yes, reasonable. What could go wrong? Looks okay. No. Let me show you again. That's the Kirchhoff approximations. Kirchhoff integral theorem, integral formula. Kirchhoff integral formula. Kirchhoff approximations. We just rewrite this equation. Equation 10.79 is an integral equation for phi. It becomes a solution for phi under Kirchhoff approximation. Kirchhoff make two approximations. Phi 1, phi and partial n vanish everywhere on S1 except in the openings. Okay, so we have a few openings, one slit, two slit. So you can imagine phi will be 0, 0, because no source is blocked by the screen. Good approximation. And phi and partial n in the opening are loss of the incident wave in the absence of any obstacle. Kirchhoff make two assumptions. One is we don't have to consider the wave. The wave comes from except for the opening. And the second assumption, second approximation is phi and the partial n. We just consider this is the incident wave without the obstacle. We make two approximations. The approximations make here work best for lambda. That is, if we have a big opening, yeah, with this opening, without this opening, no difference. So the wave will be exactly the same as the incident wave. And other regions, except for the openings, except for the holes or apertures, no contribution at all. So Kirchhoff approximations is good. Yeah, reasonable. So Kirchhoff theories work remarkably well in the optical domain and has been the basis of most of the work on diffractions. Work well. Okay. However, we encounter some problems. Okay. I was told you what is the problem. From here, and we assume S2 no contributions, and just consider S1. And Kirchhoff further make two more assumptions, and we use the green functions. That's for the outgoing wave. Kirchhoff approximations vanish on any infinite surface, on any finite surface. So phi equals 0 everywhere. That's true for Helmholtz equation. Okay? This is, of course, inconsistent with the second assumption. Second assumption assumes that if phi and partial n are 0, then the green function is good. And however, at the opening, at the hole, at the apertures, it's not 0. That's the Kirchhoff second approximations. That's inconsistent. Okay, and this equation 9.79, this one does not yield the assumed value of phi and psi on S1. Because incorrect. The mathematical inconsistency in Kirchhoff approximation can be removed from the choice of proper green functions. That is, the green function we select here is not the best choice. It's not it's not the best choice, but it's a pretty good choice. Can be removed if phi is known approximately on the surface S1 at Dirichlet green functions and satisfy green function Z. Dirichlet green function is 0 on X. Then the Kirchhoff integral becomes this one. And we can omit the contribution from S2, just calculate S1. Everything is good. We can remove the mathematical inconsistency if we choose a proper green functions. But Kirchhoff approximation is useful because we don't have to choose a proper green function. We just choose this one. This green function is good enough and is powerful for many applications. Okay, so we will use this green function. Next time, I will tell you how to remove the mathematical inconsistency with another green functions. Okay, and I will give you a special case, a diffraction of spherical wave originate from a point source at PS. Okay, and we can calculate the diffraction. And on the other hand, another case, we have obstacle here. The hole, the opening is replaced with an obstacle, and we can calculate everything. Okay, we can show you another one. And we will show you the Bobbinet principle with the without with and with the obstacle, with the opening. And this one plus this one equals this one. Interestingly. And we will talk about Fresnel and Fraunhofer diffractions to extreme, to diffractions, to famous diffractions. Okay, and eventually I will tell you on the Mars, it's completely different story. The sunset is blue sunset, and the red planet. Okay, next time I will finish chapter 10. Okay, that's the end of today's course. See you next time.